Hello, everybody. Thank you for attending this afternoon session. The first speaker is one of our sponsor from JPIX. The title is the current state and issue of IPv6 deployment in Japan.
Thank you. My name is Yoshiki Shita from JPIX. I'd like to take a moment to introduce myself before we begin. My profession is I am a fellow at JPIX, an organization that plays a key role in Japan internet exchange infrastructure. And I do some other outreach activities. And my colleague.
Before we dive into the main topic, let me briefly introduce myself. My name is Thomas Nakama, and I work at JPIX as the Connectivity Strategy Department Manager. At JPIX, I'm responsible for designing and operating the Internet Exchange Network and also planning new services on top of IX, such as remote peering, global IX connections, and cache programs. Here's today's agenda. First, I will introduce JPIX and its role in Japan. Next, Yoshiki will discuss the current IPv6 deployment status in Japan, followed by the challenge faced in IPv6 deployment. And last, Yoshiki will summarize key points and share some insights on future deployments of IPv6. JPIX is one of the key players in Japan. We provide interconnection solutions that facilitate efficient traffic by peering. Our role is crucial in ensuring seamless connectivity between different networks in Japan, and Arcadia Corporation is our parent company. This is a history of JPIX. JPIX has a long history in Japan's internet ecosystem. It was established in 1997 as Japan Internet Exchange. We have been leading the IX service provider, and JPNE, the Japan Network Enabler, was established in 2010, which provides IPv6 internet wholesale services. In 2022, JPIX further strengthened its position by integrating IX and VNE as one company. This slide illustrates the JPIX network topology, showing our connection points and how we facilitate traffic exchange across various regions in Japan. Our network architecture enables reliable and high-speed connectivity, making JPIX a crucial part of Japan's internet infrastructure. JPIX has 4 segments to connect in Japan: Tokyo, Osaka, Fukuoka, and Hokkaido. Tokyo has the most traffic with most ASNs, and peak traffic is around 2.6 BPS. If you want to see more information about the connecting organization, please check PeeringDB. JPIX has a diverse range of members, including over 100 ASN in Japan eyeball network, including cable TV, DSL, and ISP providers across Japan. Many small to medium-sized CATV networks provide local internet access, while ISPs offer nationwide coverage. Also, we have content provider and enterprise peering with us, ensuring efficient data exchange across the country. For education and research, we only have 4% from the total customers. In addition to our domestic services, JPIX also collaborates with global partners, other IXs in different regions, and resellers who can bring customers from outside of Japan to have international interconnections. JPIX has supported APAN for many years. In the Internet Exchange, we have been supporting to Japanese educational and research organization and also to international organization. If you are interested to connect to JPIX or if you need more information, please come to our booth. I will have Yoshiki to do the rest for IPv6.
Then I introduce FTTS service in Japan briefly. This slide shows the FTTS service in Japan. In Japan, FTTS services are categorized into three main types. One, full service. Second, ISP fiber service and internet service. And FTTH access line and internet service. Three categories. Three types. Full service are ISP express network operation centers to connect users to direct internet. They don't rely on entities fiber infrastructure for the last mile connection. Fiber second type are ISP lease fiber from entity east and west and separately provides internet service. And access line and internet service are ISP connected to entities point to entities line access line service by using access lines. Unlike in many other countries, Japan's FTTH strategy is more complex than commonly perceived. Let's explore why. FTTH infrastructure in Japan is complex due to two key reasons. One is legal regulation. Government imposed rule on NTT. The second, historical reason. The legacy structure of Japan's telecom markets. To understand this, let's take a look at the legal frameworks. The regulation of NTT is rooted in historical events. 1985, the privatization of NTT and liberalization of telecommunication. NTT remains regulated under the NTT law. 1999, establishment of NTT East and West, regional company. This company inherited NTT's access networks and facilities. They are restricted to regional telecommunication and telecommunications only and telecommunication service only and cannot provide global internet service. Now, let's look at the historical factors shaping Japan's FTTH landscape. The development FTTH service in Japan has key milestones. 2001, launches of Flexical leaflet service, the first NTT fiber optic internet service. The service divided into access lines service and internet service. Only IP version 4 via PPP was available in 2001. 2008, launch of Flexical Next built on NGN, Next Generation Network, based on IPv6. However, IPv6 connectivity was not available to ISPs, only IPv4 via PPPoE. This led to discussion on providing IPv6 internet access. After the discussion, the Ministry of Internal Affairs and Communications approved two IPv service modules in 2009, PPPoE-based IPv6 and IPoE-based IPv6. PPPoE-based IPv6 is similar to IP version 4, but IPoE-based IPv6 is a new method. 2011, IPv6 internet service via IPoE and PPP was officially launched. Let's dive deeper into the difference between PPP and IPoE. Here is the direct comparison between PPPoE and IPoE. IPoE is an alternative PPPoE, offering more direct and efficient way to connect to the internet. PPPoE type use IPv4 and IPv6 separately and requires manual authentication and slower performance due to tunneling overhead. IPOE type. IPOE provides native IPv6 connectivity without tunneling, supports native IPv6 and offers faster, more efficient connection to internet. However, IPOE adoption has faced sorry. Next, I show IPOE techniques briefly. In this slide, we explain fundamentals of IPO and how it differs from traditional IP over Ethernet. Key characteristic of IPO is not the usual IPO over Ethernet in 2 points. First, multiple network address on one network, one NTT-NGN network. Different ISP operates on the same infrastructure. Users are connected to their respective ISPs based on pre-assigned network address. Second, source address-based routing. The routing decision made based on the source IP address. Each user is assigned to an IP address associated with the specific ISP. This ensures that packets are directed to the appropriate ISP and then to the internet. This setup allows ISP to provide IPv6 service more efficiently while maintaining flexibility for multiple network operators within the same infrastructure. Next, we will explore the limitation of IPOE. The technical limitation of IPOE. Initially, only 3 ISPs are allowed to provide IPOE service due to technical constraints. These ISPs were required to offer wholesale service and were classified as a VNE, virtual network enablers. Our company JPIX was one of the first pioneers. 2012, Google criticized Japan's IPv6 deployment, stating Japan's IPv6 is broken. Later, the restriction was revised, expanding IPv6 ISPs from 3 to 16, and later to 10 active VNEs today. Now let's look at IPv6 trends in Japan. This shows Japan's IPv6 deployment briefly. It has gone through different phases. 2011 to 2015, very slow adoption. VNE business remained stagnant. This brings VNEs to IPv4 as a service technologies. And 2015 to 2020, IPv6 deployment accelerated. IPv4 over IPv6 emerged as the killer application. Hikari collaboration boosted IPv6 deployment and growth of video application and widespread internet use. And 2020, from 2020, COVID-19 pandemic accelerated the demand for IPv6. Remote work, online learning, and telecommunications led to traffic explosion. Firstly, I explain IPv4 as a service. that IPv4 over IPv6 are key technologies that allows IPv4 service to continue operating over IPv6 networks. Different networks technologies include MAP-T, MAP-E, DSLite, X464XLAT. ISP implementing IPv4 address sharing to optimize IP resource usage. This APAN59 page provides an overview of IPv4 as a service and different strategies ISP can adopt to manage IPv4 exhaustion while transition to IPv6. This flowchart selects CTO what technology is suitable for their company. This slide explains the different technologies used to provide IPv4 service over IPv6 networks, especially for VNEs. Key concept is IPv4 address sharing and transition mechanism. IPv4 address sharing is implemented on demand or through address plus port assignment, allowing multiple users to share limited IPv4 address pool. At the network edge, there are functions that handle IPv4 to IPv6 conversion for seamless access to IPv4 content. At the center of network, conversion function translate or tunnel IPv4 traffic over an IPv6 infrastructure, ensuring compatibility with legacy IPv4 services. Next, I explain Hikari collaboration. Hikari collaboration changed how FTT's H services are provided in Japan. Before Hikari collaboration, NTT East and West provided FTT access and ISPs provided internet service separately. Consumers had to sign two separate contracts independently. By introducing Hikari collaboration, NTT East and West wholesale FTTH lines, allowing ISP to sell bundled fiber and fiber plus internet services. This means NTT East and West shifted from a retail-focused service model where they directly contracted with consumers to a wholesale service model centered on providing service through ISPs. As a result, FTTH service churn occurred, which accelerated IPv6 deployment. In summary, Japan's IPv6 deployment has accelerated due to several factors: expansion of Hikari collaboration, growth of video application using IPv6, traffic explosion by increased internet demand due to COVID-19. Then I explain current status of IPv6 status. Google provides insight into global IPv6 deployment. According to Japan's data, Japan's IPv6 deployment rate is about 50% based on Google's network traffic analysis. Then next, we will compare this with data from Akamai. Akamai also tracks IPv6 deployment, focusing on internet traffic across various networks. The latest statistics available at Akamai State of Internet report show Japan IPv6 usage patterns. The rate is about 47%, similar to Google data. As of yesterday, Akamai reports on IPv6 penetration through multiple ISP and enterprise. And for further comparison, let's check APANIC IPv6 statistics. APANIC provides another perspective on IPv6 deployment in Japan. APANIC, APANIC's IPv6 static space offers global IPv6 deployment metrics. As of yesterday, APANIC reports IPv6 trend based on user connection test. These reports gives us an overview of IPv6 deployment in Japan. But let's now shift our focus to organization driving IPv6 expansion in Japan. The IPOE Council plays a key role in promoting IPv6 and internet expansion in Japan. This is official name and established in June 9, 2020. Our purpose is to promote internet expansion and IPv6 deployment, to improve internet infrastructure and user experience, and to support new lifestyle and industry enabled by 6. And this organization is organized by IPOE VNEs. This graph is based on data collected by the IPv6 Promotion Council in Japan. However, as the penetration rate of access network reached the target, 80%, the survey was discontinued in March 2021. As a result, the adoption status beyond this point is unknown. So, IPOE Council has been disclosing IPv6 subscription data since March 2023. Purpose of this data disclosure is encourage IPv6 compatible content development and provide objective data for policy and strategy discussion and support fair market expansion in internet industry. IPO connection statistics includes the IPO Council IPv6 depend this statistics shows subsequent rate of IPv6 via IPOE. This table and shows graph shows that IPOE per subscription number. This slide shows the latest status of IPOE connection in Japan, highlighting the steady growth in IPv6 adoption through IPOE-based service. Key trends in IPOE subscription and number of ISP supporting IPOE. More ISPs are adopting IPOE to provide a better performing and more scalable internet access experience. This data indicates that IPOE adoption is becoming a mainstream choice, supporting IPv6 connectivity at scale. This graph shows IPv6 traffic rate from VNE access network's point of view. Dual stack, by using dual stack IPv6 v4 dual stack, the COVID-19 pandemic led to a surge in internet usage, further accelerating IPv6 deployment. This shift toward data communication and video streaming highlights the need for efficient internet protocol. IPv6 deployment continues growing as more ISPs and content providers supported IPv6-enabled service. And last section, we will discuss hypercycle of IPv6 hype cycle of IPv6 in Japan, challenge to IPv6 deployment, expanding IPv6 content usage, and summary. The deployment of IPv6 in Japan has followed the pattern of Gartner's hype cycle, with key milestones along the way. Innovation Trigger, development RFC 1883 and Kami project. Peak of inflated expectation is 2000-2005. Optimism about IPv6 deployment. Through this moment is very extremely long time for 2005 to 2015. Although IPv4 address question or IPv and World IPv6 Day and World IPv6 launch. And now slope enlightenment from 2015, Hikari collaboration and increase IPv6 decrease. Now Japan is entering in slope of enlightenment for IPv6. In this slide, we will discuss key challenges related to IPv6 deployment, particularly the role of hyperscaler and the lack of domestic content support. IPv6 in hyperscaler is still growing. Major global cloud providers and CDNs have widely adopted to IPv6. Companies like Google, Amazon, Akamai play a significant role in IPv6 traffic generation. Driven by hyperscalers, IPv6 traffic is still increasing. Due to their influence, IPv6 traffic now exceeded 60% and continue to grow. But insufficient IPv6 support for domestic contents. We play ongoing activity to promote these deployment of IPv6 content. One of the key challenges of IPv6 deployment is the lack of content size support. While network infrastructure has largely adopted to IPv6, many content providers still rely heavily on IPv4. Let's explore the pain points preventing widespread IPv6 deployment on the content side. Legacy system and compatibility issues. Many websites and online services are built on IPv4 infrastructure. Upgrading to IPv6 requires investment in new systems, software, and expertise. Limited business incentives. Since IPv4-based content still function well, content providers see no immediate business benefit in migrating to IPv6. Most users access the internet through dual stack networks, allowing IPv4-based content to remain accessible. And lack of awareness and priority. Many business and developers are not freely aware of IPv6 benefits. IPv6 deployment is often not a priority in corporate IT roadmaps. Advertising and tracking issues. Some ad networks and analytics tools still rely on IPv4, making a full transition to IPv6 complex for ad-driven businesses. To drive IPv6 deployment, more effort are needed to educate content provider, demonstrate business benefits, and create incentive for migration. Next, let's discuss initiative aimed to expanding the use of IPv6 contents. IPv Council is currently working on providing IPv6 geographic information. IPv6 geographic information sharing activities provided prefecture-level IPv6 data. Demonstration experiments are planned to promote IPv6 in content delivery. Then future goals are changing format to encourage IPv6 content hosting and expansion of information providers supporting IPv6 based. As we conclude this presentation, let's summarize the key points regarding IPv6 deployment in Japan. Current status: users can access IPv6 seamlessly without even realizing it. Most users today are on IPv6 networks without needing to configure anything manually. IPv6 traffic is steadily increasing. More service ISPs and networks are enabled IPv6, leading to conscious growth in usage. And challenges issues. IPv6 deployment for domestic content is lagging. While access networks have adopted IPv6, many websites and online services in Japan still rely on IPv4. Some business professionals and academics still believe IPv6 has not fully arrived. This perception slows adoption among enterprise and research institutes. And district on data communications still treat IPv6 as an add-on. IPv6 need to integrate as a standard in technical education and training materials. Overall, IPv6 adoption has made significant progress, but further efforts are needed to drive full integration across networks, content providers, and industries. So, thank you for your time and attention.
So is there any question on the floor?
IPv4 network and IPv6 network running on the same backbone. This is first question. Question number two, if you are using IPv4 to access and you are using IPv6 to access to a site, are there any differences in terms of end-to-end delay and measurements? Thank you.
最初の質問から。ああ。こにできる。違いは、今、V4 アドレスがシェアされてるから、どんどん品質が落ちてきている。
For the first question of answer is that IPv6 on top of the IPv4, どっちだっけ IPv4 トップ IPv6 So IPv4 address is shared right now in Japan from ISP. Yeah, so that's also one reason that for IPv6.
IPv6 is still pointed end to end, but IPv4 is still now shared by many users. So IPv4 quality is now degrading.
Let me rephrase my question. Say when you access to a website, a hosting website from your home, right? If you are using IPv4 to access to the website, the speed and the end-to-end delay compared to you are using IPv6 from your home to access to the same website.
So,
are there any differences in terms of performance?
yes.
How are
yeah, the difference is this point. Home to IPv4 server rely on this equipment converting to JPIX network to V4. So at this point, IPv4 address is shared. One IPv4 address are shared by many users. So IPv4 service quality is discreting now. So that's the difference at this time.
I have two questions. Hi, my name is Tashi. But before, I would like to compliment what he just answered. If you look at APANX measurement, you will find V6 is about 7 milliseconds faster than V4 because of the same reason he just mentioned. So V6 generally to the same endpoint is about 6 to 7 milliseconds faster than V4 end to end because of all the translations that happen states on the boxes. So I hope that, so it's about 7 milliseconds.
That is theoretical.
No, it is real, it's measured.
But what I'm saying is what's happening here in Japan. Is the value the same?
So in Asia, it's 7 milliseconds. Worldwide, it's about 3 milliseconds. And in Japan specifically, it's about 1.2 milliseconds. V6 is still faster. My question. Thank you, sir. Thank you so much. That's a very big push. I was just looking at some APANIC numbers. There are a few things that stand out, and I would like clarification. Why is Japan's IPv6 capable and IPv6 preferred numbers not matching? It's about 4% to 5% difference, where a device is V6 capable, but it does not prefer V6 when it goes out. First question. So I feel there are still some end devices, maybe it's mobile handsets, maybe it's old modems, I don't know what it is. But ideally, if you have a dual stack box, it should prefer V6 out. Happy eyeballs should push V6 out first. But in Japan, what I'm seeing is your V6 capable is 62%, but V6 preferred is sitting at 58%. So that's a 4% difference of I'm capable, but I'm not using V6 to go out. So I want to understand why. One. Two. Okay, I'll let you answer that. Yeah.
流せる数%さ流してない人がいるの。なんで日本だと
あれ、V6 に対応していない機器が例えば。
機器だけどコンテンツも。
コンテンツは V6 にするウィルがないから。
So, in your case, the target content you support in your stack or IPv6 and IPv4 capable, right? So, and still the IPv6 preference is lower than
it's very weird, curious.
Yeah, it's also a device problem in Japan that there's lots of devices I think that's the reason that there's a few percents of that you can on the network side, but the device doesn't enable to do IPv6.
Yes. Okay, I'll take it offline with you during the break. So my second question, I see dual stack. I also saw some 464X LATs, NAT64, DNS64. Few problems with DNS64. It breaks DNSSEC. It's a very well-known problem because I'm a V6 only host. I want to talk to V4 only. The DNS64 lies to me. Hey, here is a record. It's not A. It's not a quad A. It's actually a record. You lie to me, synthesize, and give it back to me. So that breaks DNSSEC. So it's a well-known problem for last long time. So I wanted to know. My question is: in Japan, have you now moved on to? There's also a new concept called V6 mostly, not V6 only. So it's a very recent RFC, maybe last 2 or 3 years, where you don't rely on DNS64. There's a DHCP option 108, where if I am v6 capable, I signal to the DHCP server and say, hey, I can do v6 only. You're able to give me a v6 prefix. I can do v6 only, but I also have a CLAT capability where I have a v4 private address auto-assigned so that I don't need to use DNS64. So I just want to understand, because I couldn't find anywhere in your presentation, what's the trend? Are you still going v6 only with NAT64 and DNS64, or are you also now killing DNS64 so that you do v6 mostly? Because DNS64 is a real problem for security.
はい。いや、分かったんだけど。In mobile network, MNO way to move to mostly network, IPv6 mostly networks. For example, Docomo challenge to mostly, but fixed networks, there are a lot of classic devices, so then they cannot they cannot use IPv6. So middlebox or home broadband router supports these devices. So broadband routers support mostly network, but it's same as IPv6 over IPv4 over IPv6. And now currently, 18 million of devices support version 4 over version 6. So now we will try to fix ISP to try to doesn't try to mostly network.
Thank you. Thank you so much.
Any other questions?
If you have any questions or further information, we'll be at the booth, so you can catch us also over there.
Okay, thank you very much.
Thank you.
Thank you for introduction, Fujimoto-san. I am a sales engineer at Juniper Networks. And first of all, thank you to the APAN team for having us today. I'm honored to get the chance to speak with many of the NREN teams that are here today. At the booth, I was able to know that many of the NRENs are choosing Juniper today. And I appreciate all NRENs using Juniper for entrusting us with powering the research and education in your country and across the countries too. And I hope that we can continue working together to powering the next generation research. So thank you, everyone. So today I'll be introducing how our AI for network operations are built. And what we're working towards in the future. So before we go into the topic, throughout the presentation, I'll be using our Juniper product as an example. So I like to give a quick introduction of the solutions that are offered by Juniper today. So Juniper has both hardware and software products for all kinds of networks, from WAN networks to data center networks to campus networks. And for campus networks, we have a product called Juniper Mist. Mist is a campus solution. It's designed for managing wireless, wired switching, and SD-WAN. And we provide a cloud-based management solution for these kind of networks. And Mist has the most advanced AI capabilities within our product offerings. It has features like automated root cause analysis, chat-based network insight, automated network tuning,
and all these kind of things. And since it has the most advanced AI capabilities, I will be using this Mist as an example. For data center networking, we have a data center switching hardware. And on top of that, we have Juniper Apstra as the software part for managing the hardware. Apstra also has the ability to do AI analytics, such as root cause analysis and impact analysis as well. And one of the unique features with Apstra is that it has the capability to manage multi-vendor environments and apply AI to that. So we can apply AI to not only Juniper products, but also to other hardware vendors such as Cisco and Arista, and also Whitebox, which is running Enterprise Sonic. So this is for data center. And lastly, we have the WAN part. This is used by a lot of our NRENs today, I guess. And we have a carrier grade edge router, a core router, access routers. And we also have the AI part to this as well. It's called Paragon. And unfortunately, unfortunately, the AI capabilities for WAN is still limited due to its the WAN's nature of complexity and its characteristics. But Paragon does have some intelligent management features, and we are on our way of adding AI capabilities to WAN as well. So we're on our way. Okay, so let's get started with why do we need AI for network operations at all? And I think this may be a little bit different from region to region. So at least this is from Japan's point of view. So when I talk with the customers, many of the customers, my customers say they're struggling to keep up with the growing demand for stable and reliable network infrastructure. And I believe this comes from three issues that we currently have as a company. The first one is decrease in the number of network engineers. In yesterday's plenary talk, Keiko Okawa sensei from Soy Asia was saying we have less younger people interested in network infrastructure. And I think this is very much true. When I speak with my customers, they say the same thing. They don't have young people interested in network. And they are having less people managing their infrastructure. When we take data from the research companies, it says that we only have 10-to-1 job to applicants ratio in Japan today. And that is, I think, is a very low number. And so we have less people, but what the engineers are doing at their work today is problem two. So the engineers' jobs at companies, it's becoming a routine work. They're fixing same kind of issues every day, doing basic config changes, replacing equipment, doing version ups, etc. And this is not good when you have low number of engineers. Then what you end up with is they're doing the routine work. They don't have deep knowledge to their they stop having these deep understanding, deep knowledge with the network that you're operating, the equipment that you have. So what you end up with, you have a 1 or 2 person who has good knowledge, and if they quit, you have a network that no one can understand. Or you have to pay a lot of money to system integrators to run the network for you. So that's why I think a lot of people are now looking at AI ops as a solution to these problems. And with AI ops, our goal is not to replace you. Our goal is to take the robot part out of you so that you can focus on meaningful tasks. like in yesterday's plenary talks as well, ARNet, a gentleman from ARNet was saying that the NRENs should gather more to create a better research environment. And I think those kind of meaningful work are the things that the operators should do and not do these repetitive the things that the robots can't do as well. So that's one of the things that we want to do. And the second part is build a network where anyone can easily operate. So create a network where if you ask a question to it, you'll get an answer to. And I think the demand for AI ops solution is actually growing. This is from Gartner's research data, and it shows that 90% of enterprises will be using some AI functionalities to automate their network operations by end of 2027. And about 20% will be doing their initial network configuration via generative AI by end of 2026. So I guess although the reason for needing AI ops may be different from a company to another or country to country, we can say that there is a strong demand for AI in the network operations. But why AI now? For example, the concept of neural networks has existed since 1943. So why didn't people start using AI in 1943, but now? And I think this comes from two reasons. One, the cost of compute, and two, ease of access to AI technologies. So for the first cost of compute, computing resources needed to run AI is now cheap enough to actually build services. Flop per dollar is doubling every 2.1 years. And cost of storage has gone down about 87% in the past 17 years. I talked about our campus management solution, Mist. It's a cloud-based service. If we were to build that AI service, if we were to build Mist 17 years ago, it would have took us a lot of money to store just the data. However, the cost of storage is now cheap enough that we can store statistics from a few hundred access points for a year in just a few $100s. So the cost of compute and the cost of storage has really gone down for building AI-based services to financially make sense. But the cost alone could not have made it possible. And that's why I think we have another factor, which is the ease of building AI solutions. We have great software libraries available today, and also the power of cloud, making it possible for anyone to build an AI. For example, with Keras, which is a very popular software library for building machine learning software, when you use this library, you can write a script which does neural network training in just 11 lines of code. And then when you have that code, you need a place to run that code. Then here comes the cloud part, right? We now today have cloud environments where people can run that code without having any kind of physical hardware and at a very cheap price. There are even development environments like Google Colab, and I guess many researchers use this today, where people can run code on GPU for free. So I think all these things make it easy for anyone to build software which has AI. And I believe these kind of events have allowed us to apply AI to also all sorts of applications, such as network operations. So what are the use cases of AI for networking? And this is also straight from Gartner report. And it is said that there are 4 use cases to AI. for network operations. One, the AI-based data analytics to achieve better view of your network, do root cause analysis, find anomalies and signs of failure, and etc. And then when you do use AI to find, for example, root cause to your problems, you want to do automatic remediations, right? So the second part would be the automatic remediations. The third one would be the config generation from initial configuration to day two service configurations. And the fourth one is digital twin to test the network virtually before doing any kind of changes to your network so that there is no impact when you make that change. So these are the use cases for AI for networking. And when you put it together, it becomes a self-driving network where the network will do all the operations for you. For day zero and day one work, the operator will just need to input how the network should look like. And the AI will generate that config, test the config to make sure it works, and pushes the config to the actual devices. Then for day two, the AI will collect the data from the hardware and continuously monitor the user experience of it. And if it detects any bad events, it will generate the config needed to fix that error, test it with digital twin, and push the config to remedy that error. And I think this is the future we're looking for. So I touched on why we need AI for networking, why AI now, and how future with AI ops is going to look like. Now let's go into how today's AI ops solutions are built. I'm going to be using our campus LAN management solution, Mist, as an example. Mist has cutting-edge AI features to ensure great experience for both user and operator. It provides features like easier view of your network state, automated root cause analysis, automated radio tuning, and chat assistant for operators to troubleshoot issues easier. So this is how Mist development cycle looks like today. We have an engineering team which consists of data scientists and networking experts. This team first chooses a problem which we want the AI to solve. We base this off of common issues that we see through our JPIX support cases, as well as the problem which has the most requests on our feature request form. After we choose the problem, we go to the next step and build an algorithm to analyze the problem. Mist is a cloud-based solution, and we actually have the statistics of all the Mist customers worldwide. So we can use the global user data to build these algorithms. And we use this, we take accuracy very seriously when we are building these kind of algorithms so that you don't want a situation where you bring in an AI, get bombarded with random alerts that means nothing, right? So we take accuracy very seriously, and we try to figure out how we can achieve 95+ accuracy on the result. For example, when we build an anomaly detection, we started off with using an algorithm or model called moving average model. This gave us only a 50% accuracy on detecting anomalies, and this was not good. So what we tried next was try the ARIMA model, which provided us with 80% accuracy, better, but not good enough. And finally, we went with LSTM RNN model, which gave us near 99% accuracy. I think this obsession with accuracy is what makes our AI really good. And finally, we push this algorithm onto our cloud so that the problem gets analyzed at customer premises automatically. Then we just go back and choose another problem and start building an algorithm, push it cloud, and go do the cycle all over again. And today we use a wide variety of algorithms to analyze many of the issues that are seen in campus networks. And we've been running this development cycle for 10 plus years. And I think this is what made our AI platform production ready. Okay, so let's get more deeper dive on how exactly we analyze problems. This is an example statistical data from one of our retail customers. This shows the number of connection attempts at one of their warehouses. At this warehouse, they have 4,306 clients. They have about 189 connection attempts a day, and they have 6,522 failures a day. So it's kind of hard to say if there is a problem or not by just taking a look from this graph, right? So let's have our AI analysis. So in the back end, what the AI will do is it will focus on the failed attempts. So because that failure is the bad events on your network. We perform a Fourier transform on the raw time series data to separate the periodically failing clients and the clients which has started failing all of a sudden. So through the Fourier transform, we now have a periodic failures. And if we subtract that periodical failures from the all failures, we get the residual, which would be the possible anomalies. Okay, so let's focus on the periodic failures first. These periodic failures are often cases where the issue is on the client side. And we have to take a look into each of the client logs to see why they're failing. So I picked up 2 clients that are periodically failing. The first client on the top is always failing 24/7. So this is most likely one of the Wi-Fi enabled equipment at the warehouse. And if we take a look at the logs, the client was failing association. So we can say that this is a legacy equipment with only 11B support, and that we need to enable compatibility mode on the SSID for them to connect. The second client on the bottom is only failing on weekdays and within business hours. So this is most likely a employee PC or his or her mobile client. Now, when you take a look at this client's log, it will say that it's failing 1x authentication. So for this client, the fix is simple, where they can just fix the client certificate on the device. Now, onto the anomaly. So like I explained earlier, we use a model called LSTM RNN model to find anomalies. And to go off topic a little, we train LSTM RNN model for each site that is managed by MIST globally. What I mean by site is, for example, if you have a university campus, you would have buildings, right? So a site would be the buildings within that campus. So we train that LSTM-RNN model per each building in your campus. To do this, we spin up a GPU cluster on the cloud every week to train these models and then take them down when the training is done. And I think this is the power of running things in the cloud. And I talked earlier on why AI now, and I think the ability of doing these on-demand AI training without physical hardware, taking down when you're done with it, is the ability to do these kind of things is exactly why we can do AI as a service today. So back to our topic on finding anomalies, we can see that something bad has happened from this graph on October 27th at around 7 p.m. And these kind of events are typically network side issues, and some change on the network has broken the client connectivity. So the AI will then do a correlation of the data with the failing clients and things like client types or SSID or application, etc. And from this correlation result with the client type, we can see that it's mostly the Windows clients that are failing. Now, this could be things like driver updates or Windows update or etc. But for this customer, what they did was they pushed a client certificate update at around this time. And they were able to pinpoint the issue to this event as the root cause very fast because they had this correlation result available to them on the Mist dashboard. So with traditional networks, these kind of problems take really long time to figure out. But having AI analyze all of this automatically for you before or 24/7 makes it very easy for people to troubleshoot issues when it happens. So as you can see from the previous example, having these data is really important for AI, and we need a large volume of the right data with minimal noise for AI to deliver the accuracy needed for network operations. If we only have data from one network or networks of different expectations or different data set, like the example on the left-hand side, this is not going to work. It would depend on the problem which you're trying to solve. But in most cases, you will need multiple networks with same kind of topologies, same kind of data set to get that very high accurate AI. For example, we have a graph on the left top. The right top for you guys. So this is a data plot of the data that we use to detect VLAN configures. We don't actually use, we don't take a look at the switch configs to detect VLAN configures. We look at the traffic that is running through the APs to detect VLAN configures. And this is the data plot of that the data. And as you can see, we have many dots, right? And having these many dots will allow us to do statistical clustering of the dots to see which one is which ones have the bad VLAN configuration. So for AI to work with high accuracy, you first need a hardware that can export these good, meaningful data, and second, collect a lot of it. Okay, so we talked a lot about Wi-Fi. So let's use WAN routers as an example this time. Usually, a lot of operators today, I think NREN team is monitoring their routers today with basic ICMP ping or other basic things like SNMP to get input, output, error, interface counters, or memory usage or CPU usage. But I think this is actually not good for AI to work with. You need to be actually collecting more detailed counters for AI to work. For example, routers today have the capability to export which traffic that they are dropping and why it's dropping them. For example, our Juniper routers have a feature called Juniper Resiliency Interface. By using that feature, when the router drops packets, the router will report to you, hey, I just dropped this packet. For example, the source IP is X, destination IP is X, source port, destination port is XYZ. And also its reason for dropping them. So, for example, this packet had TTL of, for example, 1 or 0. So things like that. So why, which traffic they've dropped, why drop them? We report things like that in IPFix format. After we know that the packets were dropped, we have to figure out why, right? So we also have detailed statistics on the control plane side too. For example, we can report things like FIB installation errors or next hop resolution errors and so on. And we can actually use these information for AI to do root cause analysis. So the router will report packet loss. If it's periodical loss, then I guess it's no problem. But if you start seeing anomaly in how the packet loss is being reported, then you may have something bad going on with your network, right? So then we can have the AI analyze and correlate the loss with these control plane statistics to analyze what's going on with your network and how you can fix it. Okay, so I guess this multi-vendor question is going to pop up. So let me touch on the multi-vendor part. So the difficult part of the networks is that you may have hardware from different networking vendors, and each vendor would have different ways of exporting data and different set of statistics, right? But you still want AI capabilities to these kind of networks as well. So what you would want to have is a vendor neutral code and vendor neutral data. And I think there is a lot of ways to achieve this. And to be honest, this is actually very hard to achieve with WAN networks because there are thousands of WAN technologies and thousands ways on how you can build your network, with each having different set of statistics that you need to watch out for. So WAN networks are hard. But with today's campus networks and data center networks, there's only so much combination to it. So it's much easier to do that. So for example, with our data center automation software, Apstra, like I said, it has the multi-vendor capability to it. So Apstra can ingest data from not only our Juniper hardware, but also Arista, Sonic, Cisco hardware as well. And Apstra will ingest the raw data that's coming out from these different vendor hardware, and it will map to a common graph database and allow AI to consume that data in a vendor neutral way. And we now have, it doesn't show on this slide, but we now have a cloud-based AI integration available with Apstra. So on the cloud, it will connect with Apstra that is on site, ingest the data in a vendor neutral way, and do things like root cause analytics and impact analytics for all kinds of vendors. So today we have many tools to gather data from the equipment and analyze it. And I think we do a very good job at delivering results at a high accuracy. However, with the current technique, I think the problem is that we can only solve predefined problems where the steps to the solution is defined by human experts. Also, it will only work on specific hardware and specific topology. So how can we handle the unknown? Maybe we don't need that much high accuracy with the unknown, but we just need some ideas on the potential ways on getting things solved. And I think this is where generative AI will come in. The generative AI, more specifically, large language models or LLMs, does a very good job at getting random data inputs and user inputs, putting them together, and getting actionable insights. and they won't provide a very high accurate result like the ones by the techniques that we use today. But I think it does a great job on providing you some ideas on how you can solve the issues. For example, we already have LLM integrated on our MIST platform. So you can basically ask questions like, why did this computer have a bad MS Teams call on September 6th? And it will analyze the data and give you some potential reasons on why it was having bad MS Teams call quality. We can also use general purpose LLMs like ChatGPT, Claude, DeepSeek to do some basic config writing or solving simple issues as well. And how about WAN, right? I talked about WAN networks having 1,000 combinations. We have actually released an LLM connector for our WAN automation solution as well, Paragon. And the LLM uses a technique called function calling to fetch information regarding your network from Paragon. So for example, in this video, we have a user input of list alerts on my networks. And the LLM will fetch all the alarms that are going off in your network and create a summary view of them. And when you do this, you want to go further and ask how you can fix the alarm. So when you ask questions like, can you please elaborate more on the fan alert that's going off right now? It will give you some tips on how you can solve the alarm. However, like I talked earlier, LLMs have very high potential, but the accuracy is very bad for network operations, unfortunately. They hallucinate, they have biased output. Their output is very inconsistent. So if you have tried ChatGPT before, the answer will change depending on how you phrase the question. So the output is very inconsistent. So we will definitely need a current technique to solve problems at high accuracy. But we can also have LLM to provide you some guides on how you can solve issues. There are actually works on how we can improve LLM accuracy through RAG and fine-tuning. And there are actually research works that attempt to do this. So hopefully we will have an LLM which works well with network operations in future. However, we still have like problems that we need to solve even if we have these kind of LLM. For example, how can we collect the data, or like can a network operator operate LLMs? Some may say that we can just use the API integrations available through our LLM providers. But what we have seen with this Paragon LLM connector is that a query can go up to a few dollars a call, a few dollars a query. So if you have hundreds of network operators asking questions every day to the LLM connector, you end up with a very large bill, right? So I guess, does this cost really make sense is another thing that we need to answer for. And all these questions, I think, need answer for. And I think not only Juniper, but the industry is working on getting these problems solved. So in summary, today's AI for network operations is built using logics defined by human experts. And there is no work for all solution right now. So if you want to have an AI on your network, you will have to build a network which AI can be applied to. So to fix that error, so for the future, generative AI is being looked into by many vendors and not only Juniper, and also by operators. I think we had KDDI speak yesterday that they're working on LLM as well. But unfortunately, I don't think they can achieve the same level of accuracy as the current techniques. So we as the industry is trying to find ways on how we can improve its accuracy. Okay, so that's it to my talk. Thank you.
Thank you for your nice presentation. Is there any question on the floor?
Okay, thank you very much. I want to ask about how is the strategy in the networking data is coming very huge and very fast.
Right.
Although we use a simple machine learning algorithm
Right.
for ingesting the data is not so easy.
Right.
And the data we have two choices. See the data or processing in batch or in stream. So what do you think about that? Yeah, thank you.
Okay. So I think it would depend on the data that you're gonna be or what you're trying to achieve. So with Mist, we use both streaming and batch processing. For stream processing, it's for real-time things that we need like to solve things for things that we need to react fast to, right? For batch things, for example, access point radio tuning, they don't need real time. It can be like weekly. So for those kind of things, we use batch. So we separate the batch processing and stream processing based on how fast we need to react to that data. Does that answer to your question?
Thank you for your talk. I have a simple question. Why did you use LSTM? Because I'm curious because people in the industry always use LSTM, but in the academia we have, for example, recent findings that even simple MLP models are better for time series. So I'm really curious.
Okay. I'll need to get back on that one because I'm not a data scientist.
Okay, so for example, because you mentioned that you're obsessed with accuracy, did you
Right.
try other models?
We've definitely tried other models, but unfortunately, I'm not on the engineering side to answer that question. I'm sorry.
Okay.
But if you can shoot me an email, I can definitely ask my colleagues for an answer to your question.
Based on the four areas described in the Gartner reports about possible for AI ops,
Okay.
up to now, Juniper can handle which one of them now? Yeah.
This one, right?
Yes, correct.
Okay. So we actually have all of this today, but it would depend on which network that you're looking for. So for example, for WAN, we can only do number one. For data center networks, we can do a little bit more. We can do 1, 2, and 3.
Okay.
For campus networks, we can do 1, 2, 3, 4.
Okay. Now, besides after all your presentations, now if I'm going back home and I'm going to tell my boss, my boss will ask me a very fundamental question. How much extra money do you need? So can you roughly tell us a percentage, like without AI ops and with AI ops and the functionalities that being provided here? What percentage of the costing that I should be looking at? Thank you very much.
Okay. Good question. And I think we have sales in the back, so I need to get the sales guy to get me a number. But from what I've heard, We try to do our best on making sure that there's no big increase in how much you have to pay. So we tried we try a lot to make sure that you don't feel the change when you try to bring in all of this, but there will be a slight difference in the monthly pricing that you will have to pay. I can't tell you the exact numbers because I'm not sales and I don't know the pricing of the products that we actually sell. So, but I haven't heard that from my customers that the price changes greatly from other vendors' offerings. So I hope that answers your question. Any other questions? Okay.
Thank you very much.